Welcome back, everybody. In this next series of videos, we're looking at something a little different. Up until now, all of our discussions has, for the most part, focused on a single object. We looked at one object hanging from a string, or one object being pulled across a rough surface, one object down this tilted inclined plane. Here, we're introducing the idea of systems. We'll officially define what a system means in the context of physics, but really what this series is going over is what is the physics of motion and forces in Newton's second law when there are multiple objects connected together and therefore moving together, okay? That's what we're going to get into. Part B of this series and Part C, there's like another video with an example scenario that's worked out. Also in Part C, there's going to be another way to view, kind of another way to think about system problems. We're going to look at the first way, kind of the way that's most similar to how we've been approaching our past problems, but we'll see a little different way in a separate video, okay? Let's dive right in, okay? What is a system? Simply put, a system refers to all the objects you're considering in a problem or in a scenario. For the most part, we've always been dealing with problems that have a system of a single object. Both for projectile motion and for objects on an incline, we've only had to deal with a single object at a particular moment of time. There was only one object moving that we were dealing with, or one object in equilibrium where we were setting up the second law, for example. But as we're going to see, there might be multiple objects connected, multiple objects moving, accelerating, affecting one another, and your system refers to the objects kind of that you're focusing on, okay? Now, when these objects are existing in a given scenario, in a given problem, when our system has multiple objects that are affecting each other, there are some key things to keep in mind. And I'll demonstrate why this is true in just a second. Number one, all the objects in the system, whether it's 2 or 3 or 10, they have the same acceleration, okay? Here is an example. I'm going to pull up a website, right here. I have these two blocks. I have this red block and this blue block. And there's a variety of things that we could be doing in this example, but if I go ahead and I don't mean to move that around. If I slide this down so I can access So I have this larger mass object and this smaller mass blue object. This one is heavier. So if all of a sudden I hit start, I kind of begin the simulation, well, what happens? You see that the red box goes down. And that's not super surprising, right? Probably makes sense that that red box is going down. If I was to reset this and I made the blue box way more massive, notice I have this pulley here. Okay, we'll ignore any friction from this pulley or anything like that. Now this box has more mass. Well, now let's hit run. And now the blue box is moving down. So obviously I might have a couple different scenarios, but what do you notice? The blue and the red box, they are connected together. When the red box is moving up, the blue box has to be moving down, and vice versa. They're connected with a string. They can't both move up, not here on Earth, right? It's not possible for both of them to move down. Whatever the acceleration of this object upwards is, it's the acceleration of this object downwards. Here's another scenario, similar looking, okay? But now I have a flat surface. Let's ignore friction for here. I have some cart, so maybe it's on like frozen ice or something, and I have a hanging mass. Again, I'm going to hit start. Oh, we saw it kind of take off. We saw that this mass here accelerated downward, and this mass here, because it was connected by a string, it accelerated to the right. Whatever the acceleration of this object was, it's the acceleration of this object. So that's what I mean by this bullet point right here. This is a clue to help us solve problems. These multiple objects in our system will have the same acceleration. What else is true? Well, if we consider Newton's third law, Newton's third law says that the forces between objects are going to be the same. What do I mean by that? I'm again going to go back to my diagram real quick. Here I have this tension force. There's a tension force on this mass. This string is applying an upward force on this mass, and this string is applying a rightward force on this mass. Those are in fact Newton's third law forces. So this tension force is the same as this tension force. Or in this example, there's an upwards force of tension on this blue box. This red box is kind of tugging. Remember, this pulley is changing the direction. This red box is tugging upwards on the blue box. The blue box, by Newton's third law, is tugging upwards on the red box. whatever the tension force here is, it's the same by Newton's third law as the tension force here. Oh, I know I'm going quick, and that's maybe a lot to take in, but again, these are some helpful clues for how to set up these problems. Like all things in this class, you're going to get the most amount of practice by doing these problems. Okay, so they will have the same acceleration, and the other helpful thing is any third law forces, they're going to be equal and opposite. They're going to be the same value, the same magnitude. Remember that word? Okay, so what's our strategy? I can go pretty quick through this because it's mostly the same strategy always for our Newton's second law problems. Okay, maybe a little bit different is right here. You should recognize, I'm not saying you have to write a paragraph or anything, but recognize what's your system. Is it just one object like we're used to? Or maybe there are two objects. Maybe if it's a really tough problem, there's three objects. But how many objects should you be considering? But then we're doing the same stuff as before. We're going to draw some coordinate systems. We're going to draw some free body diagrams. We're going to break things down into components. We're going to set up Newton's second law. But what I have here in yellow, and what we're going to start our strategy as, focus on each object separately and kind of think of them individually in our setup. This will make sense in our practice problems, okay? So do all these things for each individual object. A free body diagram for each object. Break the forces down for each object. Set up Newton's second law for each object. Can these be long problems, math problems? Absolutely. But they shouldn't be terribly difficult because it's the same stuff, the same onions that we've been chopping since the very beginning of this sequence of videos, okay? And then those helpful hints I had, the accelerations are going to be the same, and any third law forces are going to be the same. Okay, let's get into the onion chopping bit. Here's a scenario. I don't have any numbers, okay? But here's one example where we have multiple objects, and you might be asked to analyze them using Newton's second law. So what's the scenario? Let's imagine I have like two carts. I have this big blue cart. Both are on wheels. We'll ignore friction. Okay, this big blue cart. But because I don't want to try and move two carts with two different hands, I'm just pushing one cart into the other. Okay, so I'm pushing on this blue cart. I'm maybe applying a force of big M. I'm applying a big force on M. And the blue cart is applying a force on the smaller cart. Let's try and set up the sum of the forces. What does that mean? Okay, I know you can't color coordinate things, but what you should do, what I strongly recommend, is you be nice and organized. I'm going to, in fact, do this for each box individually. For the box labeled Big M, let's draw our free body diagram. That's normally what we did. Well, there's, of course, a normal force on box Big M. Now, these are two different objects, so if you like using subscripts, man, today's your day. There's a weight of box Big M. What else is there? There's no friction. I'm not going to worry about any leftward friction force, but there is the force of me, or whoever this person is, pushing on the box. Aha, here is a free body diagram for this box M. Maybe I draw my little coordinate system. There's no incline in this problem, so maybe I just say right is positive and up is positive. Lovely. Now, I'm nice and organized. I'm going to set up the sum of the forces for the box that's green, the little m. And notice, individually, I'll keep them the same because that probably makes sense, but I'll say right is positive also for the little box, and up is positive. What's the free body diagram for my little box? Well, there's a normal force. It's a different object, so it should have, or at least may have, a different normal force, so label that. This is big M, this is little m. There's weight, weight little m. What else is there? There's this blue box pushing on the green box. Now, that is not necessarily the same as the force that I'm pushing on the box, but the blue box is pushing on the little box. So maybe I'll call that Fm to little m. Oh my gosh, yuck. Okay. Anything else? Oh, there's a tricky bit here. The blue box is pushing on the green box, right? That's what I have right here. By Newton's third law, the green box is pushing back on the blue box. I actually did not fully complete my free body diagram in my blue box here. I actually should have Fm to big M. These two forces, I'm going to underline them in yellow. These are my Newton third law forces, okay? And their magnitude should be equal in size. So there I've drawn my free body diagram. What's the next step in my process? Normally, it's like to break things into components. I don't have to worry about that. Normally, next, I set up Newton's second law. So let's do that for blue. So I'm nice and organized. I'm in this blue section. The sum of the forces for this still mass m, maybe I'm super organized, I label it like that. Let's set up the sum of the forces in the y direction, because that's easy. I have the normal force on big M minus the weight of big M. That equals m, and that should be a big M. Maybe I'll make sure it's super big, because that's my uppercase big M, times a of big M. And it's not accelerating up or down, so I expect that to be 0. Let's try setting up the sum of the forces in the x direction. Okay, well, what's that going to look like? I have F of big M, that's my orange pushing force, minus this green F little m to big M. And that equals big M times the acceleration of that big mass. Again, I don't have any numbers here. Just notice, what's the key idea? Notice, I'm just doing the same second law stuff as before. I don't know these values that I can plug in. Now, what you maybe recognize or maybe remember from the things I was saying earlier, whatever the acceleration of this blue box is, that should be the acceleration of the green box, because they're just pushing each other. They're connected. They're combined. They're touching. Okay, it doesn't make sense for this blue box to accelerate more. And also, let's say I knew that this force here was 30 newtons. By Newton's third law, I know that this is 30 newtons in the opposite direction, but also 30 newtons. I hit pause real quick just so I could shrink my screen a little bit. I'm also going to move my floating head. Oh my gosh, there I go. I'm going to move my floating head right here because now I can set up the sum of the forces for my little green object, my smaller mass. What does that look like? Well, again, let's set up the sum of the forces in the y direction. There's the normal force of little m minus the weight of little m. That equals little m times ay, but that's probably 0 in this problem. The sum of the forces in the x direction? Well, I have this force. I have F big M to little m. Any other forces on this? Remember, there's no friction. That's it. There's no other forces acting horizontally. So that's equal to little m minus the acceleration in the x direction for little m. So there, I mean, that's me setting it up. Remember how I talked about, if you're in my own physics class, about proving your physics. I've just proven my physics. And then maybe you could use some helpful hints. Like, remember, this force here is the exact same as this force right here. So if you knew this value, or you could calculate it right here, you could slap that into this location. Or, remember, if you could calculate the acceleration, maybe using this green equation, you could plug that acceleration here into the blue equation. The idea of systems, having a couple different equations that you can plug in and solve, that's very relevant here. Okay? So again, the key idea for this video, you might have to now separate and really think about all the different objects in your problem, but it's the same thing. Make free body diagrams, break things into components if necessary, set up the sum of the forces. But remember, these objects are connected, so they'll pretty much always have the same acceleration, and any forces that are acting between them, any third law forces, those will be the same. Those can be some helpful tricks to help you solve these problems. Okay? In future videos within this series, we'll see some more practice problems, some more scenarios, and then also kind of a different way to think about to analyze these. But that's it now. Okay? Thanks a lot for watching this video.